As 3D Native's technical and digital content specialist, Elliot is in charge of testing additive manufacturing solutions and providing feedback on their use. Through his work at 3D Natives, he has engaged with experts, industry leaders, and enthusiasts, keeping him at the forefront of the rapidly evolving additive manufacturing industry. He has a key role in multiple projects, including the production of educational content and technical articles. By leveraging his technical expertise and understanding of 3D printing technologies, his aim is to spread knowledge and passion for additive manufacturing. Let's give a big welcome to Elliot Saldukaite.
Hello and welcome to this webinar brought to you by SPE in partnership with 3D Natives. Today's subject is an overview of additive manufacturing, exploring the 7 families of 3D printing technologies. I'm Elliot, 3D Natives digital and technical content specialist, and 3D Natives is the largest international online media platform on 3D printing and its applications. We provide in-depth analysis of the market and have over 1 million unique visitors per month. Currently, we're available in English, French, Spanish, German, and Italian. We offer a variety of services such as 3D printing price comparison engines, B2B consulting and B2B brand content, event management, and much more. For today's webinar, we'll be exploring all the 7 families of 3D printing technologies. And to start, we'll try and understand what is additive manufacturing, why to use additive manufacturing, how additive manufacturing is different from subtractive manufacturing, how additive manufacturing works exactly, in which forms it comes, in which technologies, and how to get better at using additive manufacturing and mastering it for projects, and also how additive manufacturing will evolve in the future and adapt to trends that may evolve. So let's start by really understanding additive manufacturing by defining the term additive manufacturing. It's also known as 3D printing, and it's a process that creates 3-dimensional objects in the way of stacking layers upon layers of materials. So you can have different materials and you can have different ways of stacking the material and forming the material, but you're always having layers of material being stacked on top of each other. And that's being done based on a digital design file, which is a 3D model. The different advantages of additive manufacturing are that it allows for the creation of complex geometries compared to other more traditional manufacturing methods, because it's more flexible in design, so you're able to create complex parts you wouldn't be able to do with any other manufacturing technology, thus being able to customize and create unique parts. Also, additive manufacturing doesn't require molds or tooling, so it's a way more rapid prototyping method and allows for unique parts to be created without the cost of making a mold for just one part. Additive manufacturing can also eliminate the need for assembly or multiple parts. And for example, let's say on an airplane you have 10 parts to build one part of your wing. Well, with metal additive manufacturing, you would be able to replace those 10 parts by a single part, thus eliminating the need for assembly of those 10 parts to form the final part. By doing all of that, additive manufacturing can reduce material waste and lead times, thus reducing costs. Let's just try and compare additive with subtractive manufacturing. There are other types of manufacturing, of course, but really here I want to focus on subtractive, where subtractive manufacturing will be removing material from an initial block or sheet of material, thus creating waste material and being limited in complex shapes and designs, depending on where the tool head can access and remove the material. Additive manufacturing does not need to start from the material. It can build up with material. You don't need an actual block of material. You deposit material. So you are able to create complex shapes and geometries, as well as use the exact amount of material you need, just the materials that will end up in your final use parts, thus reducing material waste and saving costs. Now I would like to have a look at the 3D printing process. This is a general process, 4 steps to really understand how to manufacture objects. And of course, that process will evolve depending on the additive manufacturing technology you use and choose. But in general, those 4 steps will still be applicable. So the first step of our 3D printing process is actually to have a 3D model. So a digital file which you will then 3D print. That can be done in 3 ways. Either you model that 3D file yourself using a computer-aided design software or CAD software. So that may be, for example, CATIA, SolidWorks, AutoCAD, or some other softwares, but you can also start from an existing object you have laying around, so physical object, and 3D scan it. That itself can be done in multiple ways. So you could be doing photogrammetry, which is a technique to actually scan a 3D object, or use a proper 3D scanner to achieve 3D scanning. So you're turning your physical object into a digital file, a digital twin, which you will then be able to 3D print. And the last way to get a 3D file to then 3D print it is to use an online 3D model library. So you have a few of those. You have, for example, Sangs, MyMiniFactory, Thingiverse, Printables, and many more. So here users are actually sharing either their CAD files or their 3D scanned files for other users to use. So you have free to use online 3D model libraries, and you have also paid for. You can also share open source projects, and people will be able to remix them. So let's say you designed a superb business card holder, but people want to add their own details on it. Well, they'll be able to download it and then modify it and personalize it, or add a new feature to it and share it with the world, saying, hey, I started from that and now I added it as a feature, and people will be able to download that new version. Once you have your 3D model, you need to export it for the 3D printing preparation software, which is called a slicer. And the most used file formats here are mainly STL. So you'll hear about STL a lot in 3D printing. More and more 3MF, even though not all slicers accept 3MF yet. And for the last few months, STEP has been added to a few of them, and it will continue to be added to more and more slicers, and also OBJ, which is pretty popular, as well as STL. Our second step in our 3D printing process is the actual slicing. So here the goal is to convert our 3D model we had from the step just before into machine-readable code, so a program for the printer to follow. Most of the times this program will be G-code. So I'm sure you've probably heard about G-code before, because it's used with most CNCs or robotic arms. Some 3D printers use different code, but I'd say like 85% of 3D printers use G-code to function. So a slicer, which is the program used for slicing, works by slicing the digital model, so the 3D model we had in the step just before, slices it into different layers, and then generates instructions for each of those layers to be printed by the printer. So you will need to give it parameters and settings that will then be followed by the printer. That can be machine specifications, for example, the depositing speed, or even just the volume of your 3D printer, also the temperature for your materials, things like that. So all those settings can be put in the slicer, and then the machine will read those settings from the G-code. So the slicer enables users to convert 3D files into machine-readable and printable files, and also to add their settings, their print settings and material settings, to ensure good 3D printing. Next step is actually the 3D printing. So you take the files you sliced, the G-code you have, and you put it in the 3D printer. And this is, well, we can say the best part, because the printer is printing by itself. So if you gave it the right parameters, the machine is autonomous and 3D printing. You have many different 3D printing technologies, but all of them will be 3D printing and building the object layer by layer according on the instructions you gave it in the step just before in that slicer. Depending on the technology, the 3D printer will be depositing, curing, melting, sintering, or binding the material, which itself can be plastic, metal, ceramics, many other materials. And also the place where you're depositing that material can change depending on the technologies. That could be a build platform, a vat of resin, or a bed of powder. And last but not least comes post-processing. This one is not always mandatory. So for FDM, FFF, and material jetting especially, this step can sometimes be skipped if you don't really need it for the side fit and finish you're going for with your piece. But most of the time, and for all other technologies, you'll still be doing some post-processing, as I said, it enables to achieve desired finish or functionality of the parts. And it can include cleaning, removing support structures, sanding, polishing, and painting. Now that we have seen the 3D printing process in general, I'd like to go in a bit more into detail and understand the different technologies of 3D printing. So we've made a general classification of the technologies available and regrouped them into 7 main families of additive manufacturing. First of the 7 families is material extrusion. I'm pretty sure you're already familiar with this one because, well, this is the one where you will find filament 3D printers, so FDM or FFF. This one is used a lot for prototyping, but also production parts, jigs, fixtures, molds, and tooling. It's used in industries like automotive, aerospace, medical, and consumer goods. Second is fat photopolymerization, which is a type of resin 3D printing. It's a very precise 3D printing technology with applications in prototyping, dental models, and jewelry. Here, the industries are dental, jewelry, and medical. And the 3 most common technologies are SLA, DLP, and MSLA. And to be fair, any other vat photopolymerization technology will in some ways be based on SLA, DLP, or MSLA. So we can say those are really the 3 technologies of vat photopolymerization. Third is PBF or powder bed fusion. So here's applications are prototyping, production parts, aerospace components, and dental prosthetics, because this is a very fine and precise technology using a laser and able to print parts from polymers or metals. So the industries are aerospace, medical, dental, and automotive. As I said, you're able to print polymer. So that would be with SLS, or selective laser sintering most of the time, and metals, which can be done with TMLS, direct metal laser sintering, and EBM, electron beam melting. Next is binder jetting, and actually binder jetting uses printheads which are very, very similar to inkjet printheads, so the ones being used in office and home paper 3D printers, paper printers. But here you're stacking layers of material on top of each other, thus building a 3D object. And you're not jetting ink, of course, you're jetting a binder able to bind the powder you're using. And because this is a powder being binded by that liquid, you're able to use a variety of materials, almost any material which can be in powdered form. So you can print sand, metal, ceramics for prototyping, small parts, and jewelry. So in industries such as jewelry and consumer goods. Again, using a very similar type of printhead, still similar to inkjet printheads, is material jetting. And here it's using the same material, the same resin as vat photopolymerization. So it's a UV curable photosensitive resin. And it's very precise 3D printing technology with applications in prototyping, small parts with high resolution and accuracy like dental models. Industries such as dental, medical, and consumer goods use a lot of material jetting. And the 2 most common technologies here are polyjets and multi-jet printing. Polyjet being a technology by Stratasys and multi-jet printing by 3D Systems. So 2 big leaders in additive manufacturing and also historical companies in 3D printing. Next, going back to metals, is directed energy deposition, or DED, with applications in repair, modification, and also adding features to existing parts. because in some ways you can think of DED as a kind of welder on a very precise robotic arm. So you're actually able to build on existing metals and existing metal parts. So let's say, for example, again, going back to your airplane, the wing is damaged and you don't want to change the whole wing, where you can cut off a section and build on the section you kept thanks to directed energy deposition. So it's used a lot in aerospace, defense, and automotive, as the most common technologies are EBAM, electron beam additive manufacturing, lens laser engineered net shaping, and warm wire arc additive manufacturing. And last but not least is sheet lamination. Here, honestly, sheet lamination is less and less used in additive manufacturing, and it's in some ways a kind of hybrid manufacturing technology, because it's kind of mixed between subtractive manufacturing and additive manufacturing. You're starting from sheets of material, cutting some material off, doing the geometry you want for each layer, and then stacking the layers on top of each other. So it's still being used a bit in prototyping, architectural models, and packaging, especially with paper and cardboard, so industries or architecture, packaging, and consumer goods. And the most common technology is LOM, laminated object manufacturing. Now that we have seen the seven general families of additive manufacturing, I would like to go a bit more into detail on how to get better at additive manufacturing and sharpen your skill sets to be actually able to ensure better and replicable prints. As I said before, the printer is kind of autonomous, but you still have to give it correct settings and choose the adequate materials and orientations to make sure your prints will end up being the part you envisioned in the first place. So the main parameters and factors which can affect the quality and performance of your 3D printed parts will be the layer height and thickness. So that will mainly be for quality, because if your layers are really big, well, they'll be visible to the naked eye. Again, I'm sure you've already seen filament 3D printed pieces, and most of the time you can see that those individual layers is because they have pretty thick layer height. But also the thicker the layer height, the faster the print speed. So it's really balance of what you want between speed and quality. You also have the print speed and temperature. So depending on the technology, that could be the temperature the material is being extruded at, or the temperature of the whole environment to condition your material. The print speed could be the speed at which you're extruding the material, or the speed of the curing itself. You also need to choose the material type and properties adequately. So depending on your final application, you need to think, where will my print be used? What does it have to look like? To really choose the adequate material, depending on the mechanical properties and aesthetical properties you want. Another thing, depending on the technology again, is part orientation and support structures. So especially for extrusion-based or DED, here this is important. So you want to make sure to orient your parts correctly, because the layer are supported, well, each layer is supported by a layer under it. So if there is too big of an overhang, layers will tend to be subject to gravity, of course, and try to fall down, thus resulting in an inadequate result. So here, either you could be using support structures to make sure those layers are correctly supported, or in some cases, you can reorient your parts by as low as 15 degrees or sometimes 90 degrees, just to make sure you don't have too steep of an overhang and the print will result in success. And last, if your raw parts coming out of the 3D printer isn't what you envisioned, or you still want to improve it, well, you can do some post-processing and finishing to ensure the adequate 3D printed parts. A few other tips and best practices to actually choose and use 3D printing technologies, because just before we saw the parameters, but you also need to choose the correct technology and material you want to use for each project. So really you have to sit down before starting 3D printing and determine the intended use and requirements of the parts. And actually, you need to do that before 3D printing, but ideally, this would even be before CAD, because each 3D printing technology, the results of each of these technology can be improved via CAD and what we call a design for additive manufacturing, which is taking into account all the parameters of different additive manufacturing technologies and really implementing that in the modeling to make sure we have a correct result. So you need to research and compare the material compatibility of each 3D printing technology, because if you really want to print in a specific material, not all 3D printing technologies will be capable of printing with that material, so that can already be a limiting factor. You also need to consider the cost and availability of materials and equipment. Some technologies can be really cheap. For example, FDM, FFF, you can find 3D printers as low as $250. And with those 3D printers, you're already able to print plastic parts and achieve good results. Or you could use resin 3D printers, especially MSLA, and same, get into MSLA 3D printing for as low as $200. But here you could benefit from using a post-processing machine, which itself costs about $200 too. So total, you would be at $400 to go get into resin 3D printing technology, fat photopolymization exactly. So that's pretty affordable and easy to get into, but some more industrial technologies like DD will be really, really expensive, and you do have to have the right application to be able to use them and justify the costs, the entry cost of such a machine. Also, for each technology you use, you have to test and optimize your print settings and parameters for each material and also each application, and really know how each material works with the specific 3D printer and specific 3D printing technology. Now that we have seen the 7 families of additive manufacturing, the process, and how to better master additive manufacturing, I would like to try and get a glimpse of the future of additive manufacturing, reflect on the evolution of additive manufacturing, its impact, and see how it could evolve in the years to come. So the current trends and developments in AM research and innovation right now are bioprinting and tissue engineering, large-scale and high-speed printing, hybrid and multi-material printing, also figuring out how to make manufacturing more sustainable and develop a circular economy, and also outer space manufacturing. So there are some projects of bringing large-scale crane-size 3D printers to the moon and to Mars to actually build lunar and Martian bases and actually print from the lunar dust, thus not requiring the fact of sending material to those planets. So those are really the current trends. Also, the potential impacts and opportunities for society and environment concerning additive manufacturing. As we already said before, additive manufacturing allows to reduce waste and emissions. It also allows to produce more locally and decentralize production. So you could have labs and shops 3D printing very locally, either in your country or even in your town, rather than have big warehouses on the other part of the world. You'd be able to have maybe that'd be custom parts or replacement parts in your neighborhood or in your town. And also increase the access to customized products and services, and the access to improved healthcare and medical treatment, whether that be because you're 3D printing medical equipment or 3D printing drugs. We have seen that in the past, so it's really evolving really fast on all of this. But there are a few challenges and limitations to overcome for additive manufacturing to actually become more widespread and accessible. If those were actually overcome, it could grow significantly and be way easier to get into. So the first one is the cost and scalability of materials and equipment, because additive manufacturing is pretty cheap if you're producing just one custom part, but at scale it's not comparable to, let's say, injection molding. which is really the king here, because you're still producing each part individually. It's taking time on just one machine, so it's not very competitive with some other technologies. It would have to become way more scalable, and the cost would have to go down. Same goes for filament. Filament 3D printing is still pretty expensive compared to the pellets you can buy for injection molding or things like that. Also, additive manufacturing lacks in terms of standardization and certification, especially for applications like aerospace, automotive, things where safety is a big preoccupation. We are lacking regulations and certifications, whether that be of the material or the actual process itself, to allow for the use of these processes. Another thing is intellectual property and regulatory issues, because people are, with a 3D printer, people are actually able to manufacture from their homes. So we need to make sure intellectual property is still a thing and still respected, because if people are able to reproduce your parts and you share your designs, well, what happens if they actually make money from the parts you designed and you just gave them for personal use? So that still needs to also be better regulated. Also, there's a big technological and skills gap, because the AM technologies have evolved a lot over the recent years, and now I'd say almost any of the technologies are able to do really complex parts and produce high detailed 3D prints, but the actual users don't always know how to better use actually the technologies at best and take full advantage of them, whether that be choosing the right material or actually thinking of using additive manufacturing for an application where you never thought additive manufacturing to be the right fit, or also just designing correctly, because additive manufacturing is capable of many things, but if you have the incorrect 3D file or 3D model from the start, you won't have the most optimal result in the end. So, because this was a pretty full webinar, I would like to do a recap of all of what we've gone over and do a summary of this refresher on additive manufacturing. So, we started by defining the principle and setting the principles of additive manufacturing, learning that it builds objects from material layer upon layer. We've compared it with more traditional manufacturing methods like subtractive manufacturing, and so that it can use way less material than subtractive manufacturing. And also it doesn't require molds to produce parts. And we've seen that with the complex geometries you're able to do with additive manufacturing, you have a real potential for innovation and creativity. Then we have seen the general process, which consists of 4 steps. So you have CAD 3D scanning, or having your 3D model from a non-line 3D model library. You have the slicing, which is converting that 3D model into machine-readable code, so G code most of the time. So this is slicing. You have your printing. You can use many different technologies within the 7 main AM families. And you can post-process your additive manufactured parts. We have talked about the 7 AM families, which are material extrusion, so FDM or FFF 3D printing, filament 3D printing, VAT photopolymerization, which is very precise and uses resin, powder bed fusion, again, very precise and uses powder here, binder jetting, uses powder too, very precise and uses a kind of inkjet printer head, material jetting, very precise, uses the same type of inkjet printer head, but here you're jetting resin as for a VAT photopolymerization. And then directed energy deposition, which is a large scale, large format welder, so metal additive manufacturing technology. And actually it's being used to manufacture rockets, which have made it to outer space. Relativity Space has been doing that. They printed 85% by weight of the rockets in metal with directed energy deposition, and also a bit of powder bed fusion, and the rocket was able to go into outer space. And the last one is sheet lamination. We've also seen all the applications and industries using additive manufacturing or 3D printing. So the main ones here are aerospace, automotive, healthcare, jewelry, medical, and construction. And as I've just said, this is actually Turn 1, the rocket from relativity space, which has made it into outer space, being 3D printed in metal with DED 3D printing. So thanks a lot for attending this webinar on additive manufacturing and better understanding what additive manufacturing is. Global overview of the 7 main families of technologies present in additive manufacturing, also reflecting on the future of AM. I hope this was interesting and sparked your interest into 3D printing or additive manufacturing. Also hope you were able to learn a bit about additive manufacturing and you now want to explore additive manufacturing a bit more. So now I am open for your questions, so please don't hesitate if you have any.
Thank you. Let's take some questions from the questions window. Please click on the live discussion button and enter your questions in the questions tab. Our first question, are you planning to cover viscosity criteria?
So I have a question. Are you planning to cover viscosity criteria suitable for plastics, suitable for each of those 7 methods of 3D printing in a separate webinar? So actually, we may do future webinars about 3D printing, about the technology available in 3D printing, also the materials available in 3D printing. We also have on 3dnatives.com and on our YouTube channel especially guides and videos about different subjects and also more and more technical subjects to better get into that. So that may be a future topic indeed. Thanks for sharing. So I have another question. Can you please elaborate on the challenge in AM related to intellectual property? Is the primary challenge related to obtaining new patents to protect new technology, or is it related to finding rights to practice through existing patent landscapes? So it's a bit of both. With new 3D printing technologies coming out, for example, BCN 3D has introduced a new 3D printing technology called VLM. They are able to protect those technologies with patents, thus having intellectual property on the technology. But there are also problems with people being able to manufacture all kinds of objects from their homes and objects being available on the internet. People are able to reverse engineer or 3D scan existing objects protected by patents and use them normally for personal use, which can already be kind of a problem, but some people are actually selling those objects which are protected by IP. So it can be a real problem. So there is IP both on the machines themselves and the technologies being used, but also on the models themselves and the parts you're able to reproduce. Some designers could be doing a very specific part, whether that be a chair or a piece of art. And if someone buys it and decides to 3D scan it and share it for free online, this is a problem because this is a violation of intellectual property, and people are able to reproduce that part which was before very specific and custom made by the artist, and now it's available for anyone on the internet to reproduce with their 3D printer. So I have another question, which is it possible to print elastomers in 3D printers? So yes, it is possible. You have multiple 3D printing technologies. So for example, with extrusion 3D printing, you're able to print almost any TPE, especially TPU. Resin 3D printing, also you can print with flexible resins. You can also print an extrusion with silicone, and some elastomers, some other elastomers are also compatible with different technologies of 3D printing. Actually, it's also available in SLS. So another question is, will you offer more in-depth webinars of additive manufacturing? And here really it's depending on you, the audience. It really depends on your interest. We'll be creating content based on your interest, what you show you're interested in and what you want to be covered and better understand in the future. So don't hesitate to share your questions and also just your interest in general, whether we treat that in webinars, in events, because well, we have events through SP, but also through our additive brand at 3D Natives, or we could do videos or articles. So really, we have many different formats we can work with. So depending on your appetite for information and your interest, we'll make sure to provide curated content on all of this. But I would be very inclined to do more in-depth webinars on additive manufacturing if that is a topic you want to be more covered. Another question is, if you compare the VAT photopolymerization and powder bed fusion, which will give better surface finish? Do they undergo shrinkage? Would you need to accommodate in this process? Okay, really interesting question, actually. So in terms of surface finish, I'd say VAT photopolymerization because it's a resin and it's very, very smooth, very shiny also. It's a very good finish, but powder bed fusion is very precise too. Because it's a powder, most of the time, if you just clean it as a post-processing, it will still be rough and you'll have kind of a powdery finish on it. You'll still feel a bit of the powder left over on the print. So you can spray it with some types of resin and you can put some binders on it to make it more shiny and smooth. But most of the time, VAT photopolymerization will give off a better surface finish than powder bed fusion, like SLS, for example. And most AM technologies undergo shrinkage. I'd say the most severe technology in that case is DD, so directed energy deposition. The metal 3D printing using a kind of welder on a robotic arm, because you're at such high temperatures to melt metals, and then you go down to, well, room temperatures. You have a big delta of temperature, so there is an enormous shrinkage, which can deform your parts, warp them. But there are some programs being developed to actually simulate the 3D printing before it happens. And based on those simulations, the software is able to calculate beforehand the exact deformation it needs to then have the perfect part. So, for example, Relativity Space, when they 3D printed the Terran 1 rocket I showed earlier, they didn't print a perfect circle for the body of the rocket. They printed on purpose a deformed circle, and then when it underwent shrinkage, it was able to make a perfect circle, which was predicted by the software simulation down to just a few tens of millimeters. So it's very, very precise. And there is some shrinkage, but modern and more advanced simulation softwares are able to counteract these shrinkages. So I have another question, which is, well, thank you for the presentation. Thanks for commenting. Perhaps you can clarify in your recap slide describing applications and industries for AM that these are for production. Yeah, so for production applications, that could be for automotive, for example. So that could be for robots used in the factories. You could have end arm tooling, custom end arm tooling printed specifically for the part you're assembling on the assembly line, or to hold a specific tool. So it's used a lot in tools and fixtures for production. Also, you could do large scale prints, especially with technologies like VAT photopolymerization. With DLP and MSLA specifically, you can print large quantities of objects pretty fast, not as fast as injection molding, but here you're doing more complex parts and custom parts, and you can print a lot of them very, very fast. So it's pretty useful for that. Okay, so another question is, can you please give comments on continuous fiber reinforced 3D printing, technology, status, market demands, etc.? So indeed, continuous fiber reinforced 3D printing is a big topic, especially in FDM or FFF 3D printing, so extrusion-based 3D printing. So the idea is to actually inlay a continuous fiber, so that whether that be a glass fiber or carbon fiber, in your 3D print. So you're printing with polymer and infusing a continuous fiber to make sure your 3D print is way more resistant to mechanical forces along the X and Y axes. So again, well, FDM and FFF 3D printing is an isotropous, so adding that fiber reinforces along the X and Y axes, and you can have very tough and strength-resistant parts printed with FDM or FFF 3D printing with continuous fiber 3D printing. So here, part orientation not only helps for the final aesthetic result, but also for the mechanical properties, because given that the continuous fiber is along the X and Y axis, you really want to make sure your part is correctly oriented to have that strength really where you want it in your part. So you have to plan in advance for that, but it's a really good way to have very strong polymer parts, 3D printed polymer parts.
All right. So yeah, at the moment, Elliot, there's no more questions.
Okay.
I'll just double check, see if anything came in.
Sure.
Oh, yeah, there is one more. I'll just read it to you. It says, I believe these 7 AM technologies are also described in ASTM 52900.
Sorry, can you repeat that one?
Yeah, the question, it says, I believe these 7 AM technologies are also described in ASTM 52900.
Yeah, those 7 technologies are recognized by, I'd say, anyone in the AM industry. So this is a general classification to then go down into more technologies. But those are the 7 main technologies you can find also on other publications, yes.
Great. And another one came in. It says, can you comment on the status of non-planar 3D printing?
Yes, actually, it's a very interesting question, this one. Because as I said before, in 3D printing, you're building layer upon layer. And those layers are flat most of the time to 3D print the objects. In FDM or FFF, which is again material extrusion, you are able to manufacture objects in a non-planar way. So that means that you're actually depositing the material not on a horizontal line. You can move on the 3 axes at once, so X, Y, and Z, and deposit material on a non-planar way, so you don't have that plane X, Y plane. So this can be really useful to have anisotropous parts and reinforce the overall strength of a part in other directions than traditionally. And also for some parts, it's better to have a better finish because the layer lines won't be along the same axis. It will be very different. So you won't be able to see them from the naked eye, or they will be hidden in another way. So it can be good, for example, when building helmets. A Canadian company doing so is Coupole. They're 3D printing helmets. Actually, I think they're being used in American football, if I'm correct, in the NFL currently, in some matches. So they're being printed on FDM 3D printers in a non-planar way. And they are reinforced compared to planar 3D printing because they won't break along the Z axis.
And Elliot, at the moment, there are no other questions.
Okay.
Before we wrap things up, do you have any final comments?
Yeah, so if this spiked an interest in additive manufacturing for you, I would like to share a few more resources to dive a bit deeper in additive manufacturing before our next webinar, event, or anything else. So on 3dnatives.com, we have many different guides and articles. So I created a bit of content to refresh or extend your knowledge on additive manufacturing. So all those articles are available currently on 3dnatives.com. They're available in English and all other languages. As I said, 3D Natives is available in 5 languages, so English, French, Spanish, Italian, and German. And we have many more articles, but those are really the ones to extend the knowledge based on this webinar. If you prefer video form to extend your knowledge, we also have a 3D explained video series. So in this series, I explain many different technologies. So I've gone over 6 of the 7 families of technologies we went over today, a bit more in detail, talking about the applications, a bit more in detail, showing parts, also talking about the materials compatible and the different technologies in those families. And next, we'll go a bit more into materials compatible with all of these technologies. So this video series is not done by any means. We'll be updating it with more content to come, whether that be with materials or new technologies to come out. So you can also have a look at our YouTube channel, where we have this video series, but also many others to discover shows, trade shows, events, or even 3D printing tests we do, many things like that. And again, thanks a lot for attending this webinar. It was a delight giving it to you, and I hope you're now very interested in additive manufacturing.